Alright, so we're going to work on looking at some examples of competition between substitution SN1 and SN2 and elimination E1 and E2 reactions. First, let's just summarize a few things that we're going to use to help us as we predict the mechanisms. The first thing is the type of organohalide, or it could be a tosylate that we're working with. And the first one, if you have just a methyl halide, so that doesn't have any beta hydrogen, so that takes care of, it can't be elimination. Also, a methyl cation is too unstable, so that eliminates the SN1 mechanism. So our only possible mechanism for this one is SN2. Right now, primary, you do have the potential of having beta hydrogens that can be eliminated, so that does allow elimination mechanisms. But again, a primary carbocation is going to be too unstable to form, and and E1 mechanisms involve a carbocation. So for the primary substrates, SN2 is a possibility, and E2, because neither of these involve getting a carbocation intermediate. Okay, the ones that will be the most challenging for us will be secondary benzylic and allylic structures, because these have the potential of forming a carbocation, but also they're not so sterically hindered that the SN2 reactions prevented, or even the E2 reaction. So we can do any mechanism with those. And then tertiary, remember that with the tertiary substrate, we can do SN1, we can do E1, because that carbocation is relatively stable. Tertiary is too hindered for SN2, but then E2, remember E2 actually, tertiary is better than secondary, which is better than primary. So E2 can work with the tertiary substrate. Right, the second thing that we're going to be spending the most time analyzing is the base and the nucleophile. So if it's weak and neutral, these, if it's going to be weak or neutral, they can't involve a mechanism that has the nucleophile or base in the reaction rate. And that's, remember, SN2 and E2, the base and nucleophile are part of the rate law. SN1 and E1, it's not, so it doesn't really matter. So the weaks work fine with SN1 and E1. And then for a strong nucleophile and base, those will favor SN2 and E2 mechanisms because, again, the strong nucleophile and base can get involved, and those are part of the rate law in SN2 and E2. Now, it is possible for, with other factors, for the strong bases and nucleophiles to do SN1 and E1, but there's always going to be a priority or a preference for them to do SN2 and E2 whenever possible. Now, a couple other small things to remember as we go through these mechanisms. SN1 and E1 involve a carbocation. We got to watch out for rearrangement. Okay, the next thing to remember, for the SN2 reactions, you get inversion if the leaving group is at a chiral center. You get inversion no matter what, but it only really has an effect in the product if it's at a chiral center. And then for E2, remember that your beta hydrogen and leaving group must be anti-periplanar. And just a couple other features with this. If you have a small base, something like ethoxide or an amide, these give the Zaitsev product, or you get the most substituted double bond if you have a bulky base. And for our purposes, we're just using tert butoxide. You get the Hofmann product, which is a least substituted alkene. The last major feature I'll mention here, if we have heating, that favors elimination over substitution. Okay, now there's some more subtle details we'll get into as we go into some of the problems, but this is just a basic overview. Okay, here let's just briefly review some bases and nucleophiles and how we classify them. And we're kind of generalizing here, and there's some gray area, but if you know kind of these basics here and some generalities, this can help you predict most of the mechanisms. Right, so things that are weak bases and nucleophiles, these are basically alcohols and amines. So things to look for: neutral and just alcohols and amines fall into that category. Okay, then you have the category of strong nucleophiles and strong bases. So they're both. These are alkoxides and amides. So when you have the negative charge on the oxygen or a negative charge on a nitrogen, these can act as strong nucleophiles in substitution and strong bases for elimination. Right. From there, now we have more specific reagents. The next group are strong nucleophiles, and these are negatively charged for the most part, like Cn minus, your halides with a negative charge, sulfur with a negative charge. So unlike oxygen and nitrogen, sulfur is a good nucleophile. It's not such a good base. One outlier here is even a neutral sulfur is a strong nucleophile. And then this acetylide ion, which it can certainly act as a base, but typically it's a better nucleophile. So these generally will favor substitutions over eliminations. And then for our purposes, the only species it's just a strong base but not a nucleophile is this tert butoxide. And the reason for that is because it's bulky. That steric bulk makes it a poor nucleophile, but it's still good as a base. So hopefully, kind of generalizing here will help you, predict which mechanism to do. Okay, in this first example, let's start with looking at our halide. We have a bromide. Bromine's a good leaving group. It is secondary, so that opens up the possibility of any mechanism. Next thing we look at, we have sodium cyanide. Now remember, you can just break this up in A+, the metal and the non-metal Cn minus. Well, Cn minus, that is a strong nucleophile. Not so much a base, so that really favors the SN2 mechanism. All right, and of all the factors, the solvent is the least important, but let's go ahead and consider our solvent since we have one. DMF is polar aprotic, and these solvents tend to favor SN2 and E2 mechanisms. The protic solvents favor the carbocation mechanisms, SN1 and E1. Alright, so look and see what matches here, and really our nucleophile kind of limits us to preference for SN2. So we have a match for SN2, so that'll be our mechanism. Okay, and remember SN2 goes with inversion. And we are working with a leaving group at a chiral center. So this Cn- will come in from the back side of that leaving group and displace it. And it'll end up in the back. Our leaving group is the bromide. So there's a product for that SN2 mechanism. All right, in this next one, we have another secondary bromide. This one, again, can do any of our mechanisms. Okay, but here we have this strong, bulky base. Okay, that's strong. It's a strong base. It's not a good nucleophile, so that eliminates substitution. It's a base, so it could do E1 or E2, but since it's strong, it has a preference for E2. There's no solvent to worry about here. So our match between our species here is E2. That will be our predominant mechanism. Okay, the other thing to remember, since you have this bulky base, that will do the Hofmann elimination. So how do we do that? Well, let's redraw our halide. Okay. The carbon that the bromine's attached to is alpha. And then any carbons attached to the alpha carbon, those are beta carbons. And each of those beta carbons have beta hydrogen. This one has 3 beta hydrogen. This one has 1. Right, well, the bulky base can more easily come in and grab one of these more accessible beta hydrogen versus this one that's kind of hindered by these carbon groups. So basically the trick you can use here is use the base to grab a hydrogen from the side where there's, or from the beta carbon where there's more hydrogen. Just abbreviate the tert-butyl group. So that will come and take one of these beta hydrogen and do the E2 elimination. There's the protonated base and a leaving group. But here's our alkene product. Okay, in this one, We have a secondary iodide. The iodide's a good leaving group. Secondary can be any mechanism. Next thing, we have ethanol. Ethanol is weak, and it's a weak nucleophile and base. Right? The weak species can only do SN1 and E1. Okay, so look and see what match we have. SN1, SN1, E1, E1. Right? When you have something like this and it's pointing to both SN1 and E1 mechanisms, you generally just get a mixture of the two. So we'll say we get both SN1 and E1. Okay, the way this works is for SN1 and E1, the first step, you lose your leaving group and you get a carbocation. That's your rate determining step. So that's a slow step. All right, once you've done your slow step, then you're equally likely to do an SN1 or an E1 reaction. But don't forget, anytime you have a carbocation, look for rearrangement. Here we have a secondary carbocation, and I can do a methyl shift to get a more stable tertiary carbocation. That's the one we want to work from now. From there, we can do SN1 substitution. Just use your alcohol, attack the carbocation, okay, you add ethanol to that position, but you still have the hydrogen on the oxygen. So then you just need to remove it. Right, there's your SN1 product. Right, we can also do an E1 elimination. Okay, E1 follows Zaitsev's rule to get the most substituted double bond possible. Right, now if our carbocation is alpha, we have a beta here and on the other side. But for the Zaitsev product, you want to eliminate from the side where there's fewer hydrogen, which is right here. That'll give you a more substituted double bond. So now let's use ethanol as a base instead. And you eliminate to get this E1 product. Okay, had you forgotten about the carbocation rearrangement, you would have gotten minor products of the reaction, not these two major products. All right, here you have a tertiary chloride. Okay, tertiary can form a carbocation, so that means we can do SN1 and E1 mechanisms. Okay, SN2 doesn't happen with tertiary, but E1's okay with tertiary, or E2's okay with tertiary as well. Okay, the next thing to look at here is methoxide. Okay, this is strong. It's a strong nucleophile and a strong base. All right, the strong species prefer SN2 and E2. Okay, now the solvent, really this is a bad solvent choice for this reaction. It's a protic solvent. Protic solvents favor SN1 and E1, but that doesn't mean you can't do SN2 and E2 and just slow them down. So the key things you're looking at are going to be the substrate and the nucleophile or base. Okay, so what matches here? Well, from our base and our nucleophile, we get E2. From our tertiary halide, E2. That's what matches up. This will be an E2 elimination. Small base. Means we'll get the Zaitsev product. Okay, our chlorine is on the alpha carbon. Then our beta carbons are the ones that's attached. We have one here, here, and here. Okay, well the one at the top right, that has 3 hydrogen on it. And this one has 2. And this one has 2. So really, either of these two can be used. They'll both give a tri-substituted alkene. So we really need to consider both of those. So we'll say this will be A and B. So if we eliminate through A using the base, you get this product. Okay, let's do the same thing with B. Use a different color for B. If you eliminate through it, you get this product. Again, both double bonds are tri-substituted, so they have equal stability there. So these are both Zaitsev products. We should have written up here an E2 mechanism. In this example, we have a secondary chloride, which can do any of the 4 mechanisms. We have ethoxide, which is a small, strong base and nucleophile. That prefers SN2 and E2. Okay, so and a polar aprotic solvent that favors SN2 and E2. The match you get is SN2 and E2. Now one experimental feature, and you could draw both of these products as both could form, but typically it's found that for secondary substrates, when you have a situation like this that's saying SN2 and E2, elimination tends to be the major product. Okay, although it doesn't apply here, the opposite is true if you had a primary substrate. If you had a primary substrate and nucleophile base leaning to both mechanisms, substitution is actually favored. Right, so regardless, elimination should be favored here. Now if you were going to do this in the lab, just to hedge our bets, we would also heat this up just to help favor elimination even further. Okay, but you don't have to in this case. All right, E2 elimination, this one we have to be a little bit careful on. You have a chiral center here and here. This can lead to cis and trans double bond isomers, and that means we better make sure that we set this up right to have the beta hydrogen and leaving group anti-periplanar. Okay, so how do we do that? Well, one thing I'm going to go ahead and do up here in my structure, I'm going to draw in my other implied hydrogens. I have a back hydrogen here, an out hydrogen here. Let's just redraw this down here to work with. Okay, this is going to be a Zaitsev elimination. Here's my alpha carbon. I have a beta carbon here, but that would give me the Hoffman product. I have a beta carbon and a beta hydrogen here that will give me the Zaitsev product. Okay, so we're going to do a couple of things here. What we want is the hydrogen and the chlorine anti and both in the plane. So let's rotate these three groups. I'm going to rotate the chlorine into the plane, the methyl back, the hydrogen out. Okay, and then on the other side, I'm going to rotate the hydrogen into the plane, this methyl back, and this ethyl out. So I'm going to rotate both carbons kind of in one thing here. Okay, all of your dash and wedge groups stay in the same relative orientations as the first structure. Okay, let's do this one on the left. We move the hydrogen into the plane. We've moved this methyl down. I'm not even going to draw it in. We'll just treat that as an implied methyl. And the ethyl out to the wedge. So I'll add one more carbon to make that an ethyl. Now on the other side, I moved the chlorine into the plane. I moved this methyl group back, and then the hydrogen out. Okay, so what do we have now? We have our hydrogen group in the plane, our leaving group in the plane, but the problem here is this is syn periplanar. And we were kind of forced there because our original structure had our end-plane groups on the same, pointed in the same direction, syn. So we need to flip one of these sides. It doesn't matter if you flip the carbon with the hydrogen or with the chlorine. I'll just flip the one with the chlorine. So basically you're going to do a 180-degree rotation to flip that chlorine down into the plane. The left side I'm going to leave just as is. But on the right side, we flip that chlorine down, and by doing that, our out and back groups move to the top, but a 180-degree rotation here puts that hydrogen up but to the back, and the methyl up and out. Now we're set up with the hydrogen and the leaving group anti-periplanar. So let's use our base. To do the elimination. And then these two carbons here, those end up being the double bond. Like that. Okay, and then since you have this methyl and ethyl both out, they end up on the same side of the double bond. So on the right, let's put a methyl and an ethyl. And then your back groups, on the right you have a hydrogen, on the left a methyl. Those should end up on the same side. There's your hydrogen and methyl. And now we have the correct E2 product with correct double bond stereochemistry. Right, on this one we have a secondary bromide. That means we can do any mechanism. Our nucleophile and base is methanol, that's weak. The weak ones can do SM1 and E1. This one, we have one other feature, heat, and heat favors elimination. So comparing all of these factors, the match is E1. So the mechanism for this one E1. All right, let's draw the product. Remember, E1 involves a carbocation. Always draw your carbocation and check for rearrangement. So first step, lose the leaving group. Okay, we have this secondary carbocation, but if you do a hydride shift, we can get a more stable tertiary carbocation. Now, the carbon with the carbocation is your alpha carbon. Then the betas are all the carbons attached to that. So we have a beta here, here, and here. Now E1, remember, follows Zaitsev elimination. Meaning we're going to get the most substituted double bond possible. Well, that comes from the beta carbon that has the fewest hydrogen. Here we have 3 beta hydrogen. Here we have 2. Here we have just 1. So that's the one we're going to go with. That'll give us the most substituted double bond. Let's use our base. That'll grab this beta hydrogen and eliminate. And this one actually gives us a tetrasubstituted double bond. In this one, you have a secondary chloride. You can do any mechanism. We have NH2 minus, the strong nucleophile, and base. So that prefers SN2 or E2. From here, see what matches. SN2E2, SN2E2. Right, but remember the experimental finding for secondary, when you have a tie with SN2 and E2, elimination favored over substitution. So we're going to stick with just the E2 elimination. Now we have this chlorine on a ring, it's on a wedge. For E2, remember you need anti-periplanar. So we have beta carbons here and here. Let's draw in the hydrogens. So these beta hydrogen, we have one out, one back, and here you have a beta hydrogen back. Okay, now the ring, we're not going to make them planar, but we at least want them to be anti. NH2 minus is a small base. It goes through Zaitsev elimination. Our chlorine is out, so we have a back beta hydrogen we can eliminate from here and here. But the one down here will give you a more substituted double bond, so that's the one we're going to choose. When we do that, we get this product. Right, now here we have a primary bromide, but be careful, because you might just see this and say, okay, it's primary, that means SN2E2. But it's not just primary, it's primary allylic, which opens up the window for possible E1 and SM1. So let's say we can do SM1, SN2, E1, E2. Okay, now we'll look at our base and nucleophile. It's water. It's weak. Weak's going to be SM1 or E1. So our match, SM1, E1, SN1, E1. And when you have a tie between these two, there's really not a tiebreaker. It'll just do both mechanisms. So first, let's draw our carbocation intermediate. We lose the bromine leaving group. to get this primary allylic carbocation. So that, if you want to think about why that's okay, well, it's resonance stabilized. And we should draw both resonance structures. Okay, for the substitution, when we add water, you have the option of ending up with a product that has a di-substituted double bond or a mono-substituted double bond. Well, the di-substituted double bond is more stable, so we're going to work with this resonance structure to give us a substitution product. So we'll add water. And just in a last step, you have to take one of the protons off of water. So our two mechanisms, SN1 and E1, this is the SN1 product. Now, for the E1, if we look at this, in this first resonance structure, you have your alpha carbon, which has the carbocation. Here's your beta carbon. But the problem with that is if you were to eliminate from this beta hydrogen, you would get two double bonds joined to the same carbon, which is possible, but it's not as stable of a compound, so we typically don't do that. But if you look at the other resonance structure and say this carbocation's alpha, and we have a beta carbon here with a beta hydrogen, we can eliminate. To give this E1 product. Now this isn't something we've learned yet. This is more of an organic 2 topic, but actually when you have these double bonds, one right after another, this is conjugated. And this happens to be very stable. So conjugation is a good thing. So these would be the potential products for this one. All right, in this one you have a methyl iodide. Well, methyl can only do SN2. There's no beta hydrogen to do an elimination. The carbocation that would form is too unstable to do SN1. Then you have the acetylide ion. That's a strong nucleophile. That's SN2. So this one's very straightforward. The nucleophile attacks the carbon. You lose the iodide as the leaving group. So the product you get just adds that methyl group to the terminal side of the double bond and an SN2 mechanism.